we have our last case here, which is volume. And then we'll start looking at examples. And finally, we are at our third one here. And now we're going to talk about the volume of the container and pressure. And so again, the ideal gas law says that the gas pressure is proportional to the number of molecules times the temperature divided by the volume of the container. And clearly, this has to be 1 over the volume. So it's an inverse effect with the volume. And so what we want to do here is that I'm going to have to be real careful on how I do this. So what I'm going to do here is I'm going to do the following thing. I'm going to go in and I'm going to look at my volume, and I got to be sort of like careful on how I do this because it's easy to blow the top. So let's say that I have a situation like this. So I have particles. So because I'm going to make it smaller, what I'm going to do here is that I'm going to reduce my pressure and temperature. Okay, so here we go. So the way I'm going to reduce this thing here is that I got to ice it and keep that volume fixed here. So I'm going to ice this thing. I'm going to bring it down. Let's say that I just want a nice number. Okay, there's 40. So when I'm looking at this thing, there's two things that I got to pay attention to. I got to pay attention to the size of the container, and I got to pay attention to the pressure and the temperature, so that we're looking at a couple of things here. Okay, so now the next thing that I'm going to do here is that I'm going to reduce the volume. Look at what happens when I reduce the volume. So what I'm going to do here is I'm going to squeeze this in. Okay, so now you're seeing that the molecules, the temperature actually increased. And there's a good reason why that is here. But what I'm going to do next here is that I'm going to come in, I'm going to take a screenshot of this, and then I want to share this with you so you could see what I'm talking about. So let's go look at this thing. So what I'm going to do here is that I have two things I want to carry onto my screen. Okay, so there's this guy. And I know I haven't shared my screen yet, but I will right now. Let me just transfer the images. And so let's go look at this thing. So what am I seeing when I share my screen with you now? Let me make sure I got the right one. I believe you should be seeing my screen now. So there's a couple of things that you want to pay attention to. The first thing that you should pay attention is that we want to look at two things. We want to look at the pressure in both situations. And you could see here that this guy reads here 4.6 atmospheres. And this one here reads 14.5 atmospheres. So you could see here is, but then there's another thing here. What you're finding that this guy has a larger volume. This one has a smaller volume. So when we're looking at this, what you're seeing here is that if I reduce the volume, what happens here is that I automatically have more collisions with the walls. But the question is, why? I mean, you could see that there's a couple of things that's interesting here, is that look at the temperature, which was 40 K, and then look at the temperature, which is now 81 K. So why is that? Why did the temperature go up? It turns out that the walls of the container, as I pushed them, I did external work. So what did the work do? It increased the kinetic energy of the gas molecules. So automatically, by me moving the wall in, I increase kinetic energy. So what we expect here, so when I reduce the volume, what you're seeing here is there's the work of walls increasing kinetic energy, and we see that in the temperature, right? Where we see this in the temperature. But there's more collisions with the walls because now the particles are moving faster and have a shorter distance to travel. And as a consequence, what does that do? We end up having a higher pressure. Okay? So that's how we did that. Now what I need to do here is that I need to go back up. So what I'm going to try to do is that I'm going to try to go back up to 40K and get 44.6 atmospheres. So let's go try to do that in my in the applet. So you could see specifically why I'm trying to do what I'm doing here. Okay, so now what am I going to do? I got to increase my volume. And I got to, let's see, my pressure has to be 4.6. Wow, I think I'm going to have to be careful here. I think what I'm going to have to do here is that I'm going to have to cool this guy off to get that to about the right value. Okay. So let me get to about 40. Okay. And that's pretty close. Okay. That's pretty close. So now what I'm going to do here is I'm going to take the same situation now, but this time I'm going to do what? I'm going to increase the volume. Look at the pressure. Look at the temperature now. And look what I'm going to do. I'm going to move this out. And you could see that I have a much bigger volume now. So now I'm going to go grab the screenshot. Let me take me out of the picture. So now if I take a screenshot of this guy, what do I see? So my container has to look like this now. So now I'm going to go copy this into my OneNote. Now, this picture that I have is going to be huge. So let me see if I can make this reasonable in size. So what we'll do here is that we're going to have to compare two images. And let me go share my screen back with you now. So really what you got to think about is you got to think about the following. This is where we started at right here. So note that this is at 40K. This guy is at 4.6 atmospheres. And this guy's at 40K. And this guy's at 2.8 atmospheres. So the first thing that you want to do here is that, so note the temperature does not change. Right? Look at this. 40K, 40K. Even though the volume is bigger, there's the same kinetic energy in the gases. So that means they're moving the same speed. So this implies here is that the gases, the gas particles, are moving with the same speed. But you can clearly see when I compare this volume to this volume that this volume is gigantic, right? This really has a huge volume. This volume is bigger than this volume right here. And so now we could come in and then make our remark, which is what I really wanted to say here. And what I'm saying here is that if you look at this thing, you know what? I'm going to actually draw this up. I guess I'm going to have to draw it at the bottom. I was trying to figure out, so I'm going to come in here and I'm going to copy this just so that we could put them together. It's the same statement. You don't have to rewrite this, but here's, what did we do here? In this case, we increased the volume. And as a consequence, we saw that there was less collisions. And the reason why there was less collisions is that they're moving slower. And they have to travel farther to actually do that. And therefore, they have a lower pressure. And so the ideal gas law is telling you that that's exactly what should happen. And you can see where this is exactly the case here. So again, we ask our question. What creates the low, or maybe I should say the lower pressure region? And the answer is here, we just have to, what? We increase the volume. And that's all that the ideal gas law has to say.